So, structural analysis of a 3-axis CNC machine. Well, I promise to keep the math to an absolute minimum, and I don't think it will get too complicated. But first, why? Why do I do that? The answer is pretty simple. Most guys who build a CNC machine, they buy very big bearings. And I'm unfortunately in the situation where I bought some quite shitty SBR 10 bearings, and after receiving them and having a look at them and doing a structural analysis of them, I realized they might not be enough for what I want to do. Links to everything, as always, down in the description. Then I searched the internet high and low for some information, basically to calculate the load on your bearings and your CNC machine, depending on the dimensions of the CNC machine and actual your cutting forces. But I only found one site, link again down below, and well, I found it lacking. So basically I will use very simple statics methods to calculate the load on my bearings, depending on the load. Let me turn that around. It's not quite finished, that one. Depending on the load, cutting force I have on my tool. And this little guy made from, well, you can guess it, old CD-ROMs, and yeah, this is actually part of, if you still know what that is, of a floppy drive. So 2 CD-ROMs, 1 floppy drive. Yeah, we can use that as an kind of an example. Today I want to calculate, as a first step, the load on my X bearings, the upper and the lower one. Yeah, that's my X-axis on the gantry. When I put Z force on my cutting tool, that is basically drilling down into my material, and that results in a force pushing up on my spindle axis. So, as I said, it's not finished yet, my little one. Yeah, so let's dive in. For static calculations, you normally simplify your machine. You make a little model of it. And so if you look at the CNC machine from the side, you have the upper and the lower bearing. The spindle, we don't need it today for today's calculations. And you have the whole Z assembly, and somewhere you have your spindle axis. So we basically have 2 dimensions that are of interest. First is the distance between the spindle axis, or the tool center, to your upper and lower bearings. And second, the distance between your upper and lower bearing. That's all what we need for the moment. It might be more complicated if we go to Y forces on your tool and finally Z forces pressing from the side. X forces, sorry, pressing from the side onto your tool. So let's put that one away. And look what we have. So basically we can have an upper bearing and a lower bearing, and we have a distance between them, and then we have somewhere our spindle axis with the tool center at the bottom. And our cutting force, I said we are talking about Z cutting force, is basically pressing against our tool, bottom up. So this is one dimension we are interested in on the Z-axis, and I call this simply, that is ZX, or that's the dimension between my lower and upper X bearing. And I simply call that ZX because it's the distance on the Z-axis of our machine. Just for orientation, we are looking now at this from the side. So this is our Z-axis, and here that would be our Y-axis, and we're looking directly, these are the X bearings, directly onto our X-axis. So as I said, that's simply the distance on the Z-axis between our X bearings. And the second dimension we are interested in is the distance of our Y-axis, on our Y-axis of the tool and the X bearing. That's all what we need dimension-wise. Now I have a given force on the tool on the Z-axis. F is for force, T is for tool, Z is for Z-axis. Now I want to know what forces will be exerted on my bearings. There are many ways to do that. One possibility is simply to enter the force on your tool, and sorry, I have to rotate this by 90 degrees. So basically here the upper part, that is our spindle axis. And there's a link to that software down below. Unfortunately, it's in German and it's a Java applet. But yeah, that's the one I found, and that was free. So basically, we define our dimensions. In this case, yeah, I already drawn it. That would be our Y from the tool. Our tool is hanging somewhere here. From the tool to our X bearings, and we have here our two X bearings. So this dimension would be on the Z-axis, the distance between our X bearings. And this is normally for civil engineering and a tool, and what I just gave it to work on is basically a rigid rectangle. So that x is the length of 1 and y tx has the length of 1, and I set my force on the tool is also exactly 1, on this case 1 Newton. By the way, if you are not familiar with the basic concepts of statics and don't know about force triangles, have a look at my static analysis of SBR10 bearings. You don't have to watch the whole clip. I've put a link with a time mark down below where I just explain the basics. So 1 Newton comes here. I give the basic dimensions, and the rest, well, is calculated by the program, and it gives us for the points 3 and 4, which are my bearings, the forces exerted there. So for point 3, that is here on the x-axis, that is, well, because I turned it around, sorry, but the program thinks that's the x-axis and that's the y-axis. So for the z-axis, it's 0.44. So basically the reaction is about half. So approximately 0.5 newtons. And on 0.4, which is my other bearing, we have 0.55. So also here we have a force of approximately 0.5 newtons. And then it calculates as two more forces. The first one is again on point 3, which is -1. So downwards here, -1 Newton. And here it calculates something of +1 Newton. And now, if you remember the force triangle stuff, you can go in and well, basically construct and measure, if you do it with a ruler, the resulting force on the bearing. Which looks about that. That's an eerie result, and unfortunately, if you're using such a software, it doesn't explain how it how this force will result in this force. It just does some numerical methods. It also won't gives you a simple method of changing your dimensions, and yeah, basically if you change your dimensions or you change your force, you have to insert your start data all over again and do the software do the calculations again. So that's not exactly what I wanted. So here comes the statics. So How can we tackle that problem? I already told you that basically these two dimensions and the force is all we need to calculate the force here on our bearings. And if you remember the force triangle stuff, again, link was down there, and principles of statics, that should be quite easy. So I draw here my machine, which is basically only a square. And let's make that 5 centimeters and 5 centimeters, and again roughly 5 centimeters. So that's my machine with the dimensions y, tx and zx. And my force, which, well, is coming from here, make it 5 centimeters in length again. That's my F tool X. And now we're kind of stuck. I mean, we have here the lower bearing and the upper bearing. And if you remember, one principle of statics was to calculate an equilibrium of forces so nothing moves. Everything is static in an equilibrium. And I think one of the simplest examples was tug war, a game of tug. So if that is our line, our two teams, if they pull exactly with the same force in opposite direction, they won't move. And that's exactly what we want in statics. We want to calculate the forces so that nothing moves. Unfortunately, if we have a look back at my little CNC machine, obviously I can press here, do whatever I want to that axis, and nothing will move because our bearings fix our whole assembly in space. So there nothing can move. So basically we have a little problem with statics. And in statics there are formal ways to determine if something can be calculated or can be not calculated easily. And if it cannot basically move by principle, I mean, you can apply forces, force whatever you want until it at some point breaks. Yeah, we call that system indeterminate. Yeah, that sounds negative and makes things a little bit more complicated. As I said, there are formal ways to not to calculate but to determine if a static system is indeterminate. You count basically your nodes or degrees and freedom and stuff, but yeah, it's basically a simple definition is if it doesn't move until it breaks, then it's indeterminate. If it can move like a game of tug before braking, yeah, then we're good. But in our case, we are not good. And one approach you can take here is to simplify the whole system, or to give it more degrees of freedom. Let's say this is actually still our linear bearing, but we wouldn't have a linear bearing here, but only a point bearing pressing against our ZX assembly. Then we could have some movement. I mean, the whole thing could either go that way if there's a large force here, or it could go that way, rotate around that point if that force would be greater than the force of our bearing here can exert. And that's actually something new. That's called a momentum. So, and since we are rotating around that bearing, we will have that force Ftx will result in a momentum around that point. And momentums are not really complicated. A momentum is basically the force you have multiplied by the length of the lever you have. So our momentum here would be that force Ftx times the lever we have, Ytx. And sorry, I just saw this is obviously, we're pressing here along the z-axis, Ftz, of course. Makes it much easier to understand, doesn't it? Ftz. And now our upper bearing has to counter this momentum. That is the momentum or counter momentum in the other direction exerted by our bearing up here is basically must be the same, and it's the force exerted here and times Zx. The length of our lever. And now we can simply calculate what F is. I mean, this term and this term are basically the same, so yeah, F is Ft Z times Y T X over Z X. And in our simple example, there's a reason I choose Zx and Ytx to have the same length. This is basically 1, so we have the same force here. So I can, and I will make this green because it counters the momentum. Our bearing has to exert a force, same magnitude, so a line of the same length, in this direction. Now we have a static equilibrium, yeah, nothing rotates, everything is fine. And well, the question is, what force does that bearing has to take? And yeah, now we simply have to do a force triangle. You remember, if the forces all meet in one point, and they do in that case, we can simply say, okay, the resulting force this bearing has to take is simply the diagonal here. Or you can, yeah, saying that either, yeah, I will just repeat the forces here again. Also remember, you can, as long as the forces in a force triangle join in the same point, you can move them around. You can't change the direction, but you can move them around like you want. So this force here neutralizes these forces. And it's easy to see why that is. I mean, if we are pressing here and we are pressing here, we basically try to move our whole frame away. So this bearing has to pull the frame into the same direction. And yeah, that would be a solution, but it's not the same solution as obviously our, I put it the right way wrong, the right orientation as our software has given us. And that's of course because I omitted, or let's say that's only half of the truth. We simplified the system. We said, okay, this is no longer really a linear bearing, but it's only pressing in exactly one direction. And I speed that up. If we take a second model, and now I say, here I have a linear bearing, and here I only have a bearing pressing in one direction. Then I have again my force Ftz, but this time the force will try to rotate the whole thing around this bearing. And interestingly, the lever we have is the same lever like before. It's Ytz. So nothing new there. So we have to counter here the same momentum like before. Only this time the force goes in this direction. Yeah, it's the same formula. It's only the other way around. Yeah, I'm pushing up here and try to rotate in this direction. So I take the lever with the same length and push here to counter that rotation. And the force our linear bearing up here has to exert is again the force triangle. So this time, let me take the blue, it has to pull in. And it's also clear to see, just move that around, we're pushing upwards here and sidewards here, so we have exactly a diagonal force pulling our whole assembly in the opposite direction. So now we have two solutions, and both seems to work. So what's the truth? The truth is actually, and that's called a superposition, we take both solutions and we mix them. And maybe I should do that on another sheet of paper. And if we mix our two solutions, or we basically take the average of our two solutions, I have again my square, which I do 5 centimeters on each side. We have our force on our tool. Which stops here, of course, 5 centimeters, sorry. So, and now we take really just the average. So we calculated an F here with Ft set, so the force of the tool. And we have that formula, and we just take half of that. So we have a force going into that direction, which is only half of what we initially calculated. And we also halve that force here. Yeah, we're simply taking the average of the two systems. And that might be considered a shortcut if you do the real math, but I'm okay with shortcuts when I get a result. So that's half, and the new formula, yeah, that was basically the same for the upper and lower, is that F is F T Z and Y T X over, and we need only half the force, 2. That should be a 2, sorry. 2 ZX. ZX. Now we just need to add those two forces, and we basically need to halve them, and I will put that force into using force triangles again into an X and a Y force. Yeah, this is my smaller triangle. So if I put that in for the lower bearing, we have here an additional force. Yeah, goes into the right direction, so they basically add up. And we have a force half the length, so 2.5, going down. And up here I also take half of it and get single components for X and Y. From half of the force, which is, yeah, half the length here. And this also adds up to a result the whole length, 5 centimeters, the same length as here. And we need, what am I missing? Half the downward force here. No worries. At the end I will show you a nice drawing with the formulas and everything. So that's the result from taking two approaches and doing a superposition, or basically taking the average of two results. And if we compare that to what our software calculated, yeah, basically 1 Newton upwards, 1 Newton here, 1 Newton here, and 2 Newton downwards. We say, well, it's exactly the same. And the slight differences, this is not exactly a half. The software calculates here slightly, values that slightly deviate. And the reason for that is that it's simply using another method for calculation, a method which implies that basically our body here can deform. And I will omit that little detail. It's a shortcut, yeah, but we don't want to do a finite element analysis. We just want to know the forces on our bearings. That's nice so far, but it's a little bit complicated, and actually you can do it a little bit more simpler. We already worked with momentums for our solution, and I will draw that one a little bit bigger. So our CNC machine will be represented by a square. Again. And we have our tool force on the z-axis, which are also 5 centimeters long. Yeah, F tool on the z-axis. And we have our two bearings, upper and lower X bearings. And the dimensions are basically the same. We have here, this is Y between our tool and the X-axis, and this is basically on the Z-axis, the distance between the X bearings. What you are allowed to do in statics when you are calculating momentums is you can basically freely choose what's your center of rotation. And again, this is another shortcut. We choose our center of rotation exactly in the middle of our two X bearings. So basically this is ZX half and this is ZX half. And our momentum around here, caused by the force on our tool, will be exactly the same. I mean, we just want to know how long our lever is. Our lever in this case is up here. Yeah, the force of the tool on the tool is going up here. That's our lever we have around that point of rotation. And we already calculated this. The momentum is Ftz times length of our lever ytz. Okay, and our counter momentum, which is produced basically by two forces. I mean, we are rotating now this way around. So to counter this, we need a force that is pressing here in this direction, yeah, the other way around, and pressing here in this direction, this way around. So our force to counter that is our unknown force, which we want to know, the force on our bearings, times 2, yeah, because we're pressing 2 times, we have 2 levers which are trying to rotate our axis, times 2 times zx over 2. And yeah, and again, this we can just forget about the 2 by 2, and in result we come to exactly the same formula without all the hassle. So we have F is Ftz while ytz over z, zx. And for my special machine here, this is actually, yeah, this is 1 or 10 centimeters, and this is 10 centimeters. I'd say it's 1 and 1 because it's the same size. This is basically F. So our counter forces are exactly the same size as the force exerted on our tool. So this would be 5 centimeters. And up here it's only also 5 centimeters. And if you have a look at our first approach, where do I have it on the paper? Here. That's again exactly the same. 5 centimeters, 5 centimeters, 5 centimeters, 5 centimeters. So yeah, it yields the same results. And now comes another little shortcut trick. We have still, so we have neutralized the momentum. And another technique in statics is you can basically handle momentums and linear forces completely separately. So we handled the momentum, now we still have a resulting linear force going upward. And since we have two bearings, and now, attention, shortcut, we need two forces of the length of half that length, 2.5, going downwards. And the formula for these forces would be simply, we have two bearings, this is simply that F is F T Z over 2. And this formula-wise, that looks really, really simple. And yeah, I put that in a much nicer drawing, which we'll have a look on now. So here we have the same again in a much nicer drawing. We have, at least for the drawing, our square, which represents our assembly of x-axis, z-axis, and the spindle motor. We have our spindle axis here. We have our upper x-axis guide rod and our lower x-axis guide rod, and we have our rotational center for our momentum, which is exactly at the center of both guide rods. We have our force exerted on the tool, and ignore for the moment the dotted forces. Our tool center is somewhere down below, we don't really care. We have our distance between our tool and our upper and lower guide rods. And we have, of course, the distance, and sorry, there's a mistake. I called that only ZX. Our distance on the Z-axis. And again, this is a side view on the X and the Y plane. So we're looking, getting back to my CNC machine, we're looking at it from the side. Now we already calculated our different forces. Or let's start with a simple one. The forces that are along the Z-axis. which is simply exactly half the force of on our tool. Pressing upwards, they are pressing downwards. And the formula is simply, yeah, that's our tool on the force on the z-axis, half. Now on the y-axis, we have also calculated that via the momentums. So the momentum exerted by the tool center goes this way around, and it's basically the force on the tool times the lever. And we have calculated the counter momentum created by the upper and lower bearings, which go in this direction and follow this simple formula, which is simply these forces times the distance between our upper and lower bearing. Yeah, and we have put these two momentums together and get finally to that cute little formula, which is our forces are actually the force on our tool times that lever over that lever. So already here we can learn a little bit of something, but it's really trivial. These forces will get smaller when you increase the distance between upper and lower bearing, which, yeah, it's intuitive because our lever will get longer, so the bearings don't have to press that hard to counter the momentum caused by the force on our tool. Yeah, and as a summary, you can also calculate the resulting force, which is simply, yeah, force triangle, between these two forces, the resulting force, which is the thing that we are really interested in, the resulting force on our bearing. And that formula looks a little bit complicated, but it's really not. It's simply it's Pythagoras. So I mean, this is a rectangular triangle here, and we have the length of both sides, which is the force along the z-axis on the bearing, and the force exerted by the bearing, and the force along the y-axis exerted by the bearing. So, and Pythagoras is simply say that the longer side squared is the two shorter sides squared summed up, and this is simply, and there's where this term is coming from. This is x is the square of y squared plus is the root of y squared plus z squared. But yeah, I spare you the algebra. That's basically our result. And yeah, as expected, this term, we find it here again. So it's still true, the force will be smaller if we make the distance of the between the bearings larger and keep our spindle axis as close to the X bearings as possible. And last but not least, we have for the resulting force also an angle of attack. basically trigonometry for a rectangular triangle. And yeah, that's the result. And what we can do with that now is I could take, for example, my CAD drawing of the machine I plan to build and put in the dimensions of the formulas, and we should get, yeah, some result. So, for the machine I want to build, and these would be the measurements, so between spindle axis and my x-axis bearings I have exactly 100 millimeters. Don't ask me why. Between the x bearings themselves I have 118 millimeters, and my cutting force downwards is 188 Newton. Sorry. So I can now put these numbers into these formulas. Yeah, simply take a calculator, and then I get resulting forces of 184 newtons on my bearings at an angle of 31 degrees. That's simple. I told you to ignore the dotted forces for the moment. The dotted forces are in case you're not having pressure upward exerted or cutting force upwards on your tool, but your tool is dragged downwards. Now you can say that never happens. One example comes to mind where it might happen. For example, you're drilling down into the material, your spindle stalls, your tool got stuck, and you're not around to press stop on the machine, and the machine tries to retract the tool, moving the z-axis upwards, and your tool is stuck, and well, my z-axis will be able to exert 188 newtons. So yeah, there are cases where this can happen. Yeah, or you have doing some kind of weird hole. Let's say you have a tool that is formed like that. And now you're cutting sideways into the material. And then you move the whole shebang upwards. So yeah, you can have resulting pulling forces on the z-axis. Not often, but you can. And well, it would be a shame if your CNC machine falls apart if that happens and you haven't calculated for that. So anyway, the dotted lines are the exact reverse, the mirror image of the forces we calculated. The same formulas basically apply. And if I take now my, again, in the video, my not very trusty SBR 10UU linear bearings, they have the oddity that at least I haven't looked at only single bearing so far, that they can only take forces on within 180 degrees, and they are not able to take any forces outside that 100-degree area. So forces coming from here are okay, but a force coming from here is, well, the death. Not the death, but it will then ride, instead of the balls of the bearings, it will ride on the bearing material itself, and yeah, probably get damaged. So back to my machine, which is the drawing is in scale 1 to 2. And yeah, I could work. Well, I would have to. You can change the bearings inside, so I can put it this way. Simply, yeah, okay. Simply in your hand, turn it around. So I could install them this way, but there's no way, you see my drawing, that I can install them this way. Sorry, other way around. This would not work at all, because as I said, if you got a negative force on your spindle, forces would come from here. Yeah, so looking at the forces just on the tool on the Z axis, I can see that this is not working out. And I mean, this is a good result. I mean, you build your machine, and the first time you take it under real load, it falls apart. That would be a little bit of a disappointment, wouldn't it? Anyway, more to come. We have still to calculate forces on the y-axis on your tool, and forces on the x-axis. Well, next time, forces on the y-axis, I guess, and I have to have a closer look at these guys. Maybe I find a solution there. Yeah, thanks for watching, thanks for your patience, and I know it's a little bit intense, that static stuff, but yeah, hopefully see you again.